Our goal in this lab is to use coffee cup calorimetry to experimentally determine the enthalpy change for two different aqueous reactions. This data will then be used in conjunction with Hess's law to determine the enthalpy change for a chemical reaction not easily studied in the lab setting. The reaction of interest, which is the one not easily studied in the lab, combines gaseous ammonia and hydrogen chloride gas to produce solid ammonium chloride. This reaction cannot be studied using coffee cup calorimetry as the reactants and products are not aqueous. Bomb calorimetry also does not apply as there is no combustion involved in this reaction. Hess's law tells us that the change in enthalpy for a reaction is the same regardless of whether it's done in one step or several steps. The following four reactions can be added up to give the desired reaction, and therefore they can be viewed as steps in conducting this reaction of interest. The change in enthalpy is known for the first two reactions, and we can use coffee cup calorimetry to determine the change in enthalpy for the last two reactions. The third reaction can be conducted as described by the balanced chemical equation. Specifically, aqueous ammonia and hydrochloric acid are directly combined, and the change in temperature for the resulting solution is measured. The fourth reaction, however, must be studied in reverse. That is, solid ammonium chloride is dissolved in water to produce the ammonium and chloride ions. The change in enthalpy for this dissolution reaction will be equal in magnitude, but opposite in sign to the target delta H5. Once the experimental changes in enthalpy, delta H4 and delta H5, have been determined, an experimental value for delta H1 can be calculated based on Hess's law. The experimental value can be compared to a theoretical value for delta H1, which is calculated using enthalpies of formation. Enthalpies of formation are readily available in reference books and are also reported in the lab manual. In this experiment, our calorimeter essentially consists of double styrofoam cups with a styrofoam lid and the temperature sensor. The experiment begins with a calibration run to determine the heat capacity of the calorimeter. The premise in making this determination is that for any aqueous chemical process, while most of the energy is lost or gained as heat by the surrounding water solution, some of the energy is absorbed or released by the styrofoam. This quantity of energy can be related to a defined heat capacity for the calorimeter. As shown in the diagram, the calorimeter has been placed on an electronic stir plate and a magnetic stir bar is mixing the 25 mL of the cold water. A 25 mL aliquot of hot water is added to the cold water, and the change in temperature is monitored as a temperature versus time plot. For clarification, the words hot and cold are simply used to distinguish the different water temperatures. Clearly, a temperature of about 20 degrees Celsius is not particularly cold. Because the initial temperatures are known for the hot and cold water, and after mixing, the liquids come to one final equilibrium temperature, the energy lost by the hot water and gained by the cold water can be calculated. Any energy not accounted for, therefore, must have been absorbed by the calorimeter. In the lab, Scott has already pipetted 25 mL of cold, approximately 20 degrees Celsius, deionized water into the calorimeter. A magnetic stir bar is mixing the liquid. Scott has pre-warmed some deionized water to about 50 degrees Celsius and now pipettes 25 mL of this into a small beaker. The alcohol thermometer indicates that the temperature of the hot water is now close to 40 degrees Celsius. Scott taps the start button on the LabQuest 2, ensures a stable initial temperature, and then transfers the hot water to the cold water. On the LabQuest 2 screen, we see the dramatic increase in temperature, which corresponds to the point at which the hot water is added to the cold water. When this first run is completed, it is stored for analysis later in the experiment. Notice that the LabQuest has automatically changed the scale of the y-axis. This allows us to see the change in temperature better. It is not shown here, but the calibration run is repeated one additional time. Data is now collected to determine the change in enthalpy delta H4, which is for the reaction of aqueous ammonia and hydrochloric acid. A volume of 25 mL of 2 molar hydrochloric acid is pipetted into the calorimeter. The temperature versus time graph is started. After a stable initial temperature is obtained, the reaction is started by pouring 25 mL of aqueous ammonia into the hydrochloric acid solution. In the lab, we see Scott perform these steps. A volume of 25 mL of 2 molar hydrochloric acid is pipetted into the clean and dry calorimeter. A volume of 25 mL of 2 molar aqueous ammonia is pipetted into a second beaker. The temperature versus time graph is started. After a stable initial temperature is obtained, the reaction is started by pouring the 25 mL of aqueous ammonia into the hydrochloric acid solution. On the LabQuest 2 screen, we see the dramatic increase in temperature, which corresponds to the point at which the aqueous ammonia is added to the hydrochloric acid. When this run is completed, it is stored for analysis later in the experiment. This part of the experiment is repeated one additional time. In the last part of the experiment, data is collected with the goal to ultimately determine delta H5. Recall, however, that the reaction is run in reverse. That is, the change in temperature is measured when about 3.5 grams of ammonium chloride is dissolved in 50 mL of deionized water in the calorimeter. Therefore, the follow-up calculations will initially solve for the negative delta H5. Of course, this can easily be converted to delta H5 by simply changing the sign. In the lab, we see Scott use a graduated cylinder to transfer 50 mL of deionized water to the calorimeter. About 3.5 grams of ammonium chloride is weighed on the top loading balance. Scott taps the start button to start the temperature versus time data collection. When the temperature has stabilized, he adds the ammonium chloride to the water. On the LabQuest 2 screen, we see the dramatic decrease in temperature, which corresponds to the point at which the solid ammonium chloride is added to the water. When this run is completed, it is stored for analysis later in the experiment. This part of the experiment is repeated one additional time. As a follow-up, each of the runs are analyzed to find the maximum change in temperature. The approach is seen here for the first calibration run with the hot and cold water. Analyze from the top menu is selected, then Statistics, and finally Temperature. The panel on the right-hand side provides the minimum or initial temperature and the maximum or final temperature. Subtracting the initial temperature from the final temperature gives a positive delta T value of 9.5 degrees Celsius. A similar approach is done for the data associated with the aqueous ammonia and hydrochloric acid reaction, with the first of the runs as an example. For the dissolution of the ammonium chloride, however, note that because the temperature of the solution dropped, The maximum temperature is actually the initial temperature. When the change in temperature is calculated as final temperature minus initial temperature, a negative value will result. It is important to incorporate this negative delta T into your calculations. After watching this video, you will be provided in Moodle with a complete set of data for all 3 parts of this experiment.